The next series of lectures will be quite a change from what we've seen to this point. We won't be dealing with synthesis, we won't be dealing with reagents. What we're going to be dealing with is looking at the ways in which we characterize or identify organic molecules. And so we're going to be moving into Chapter 15, and we'll be talking about infrared spectroscopy as well as mass spectrometry. And so we'll begin talking about infrared spectroscopy. And to define it, IR spectroscopy is essentially the measure of vibrations of a bond. And what this does is it provides us with functional group information. And it tells us what kind of functional groups are involved or part of the molecule that we're interested in. Now, to understand at a fundamental level what's going on, we have to understand that the energy of a energy is often associated with the equation where we can relate energy to Planck's constant times the speed of light divided by the wavelength of that light. And so what we see is that there is an inverse relationship between the wavelength of a particular energy of light, between a wavelength and the energy. And so what we have here is, let's say, a wave associated with a particular energy. And what we see is that the wavelength is the distance between the repeating patterns of that wave. And so we also know then that the wavelength is actually inversely proportional to the frequency, and that the frequency is essentially the repetition of that wavelength. So it's like the number of cycles. And so from here we see that the frequency in terms of this, the wavelength is actually inverse. So the bigger the wavelength, the smaller the energy. Is that there is a direct relationship. If we replace the frequency with the wavelength, what we see is that there is a direct relationship between the frequency and the energy. And so that energy equals Planck's constant times the frequency. So this is essentially what we're going to be measuring when we're looking at our infrared. And so we measure these in reciprocal centimeters. And again, so we see this, that the shorter, the bigger the frequency, the bigger the energy. All right, whereas in the previous slide, so what we're left with here is an understanding of the frequency and how it's related to energy. And the frequency that we're interested in is the frequency of light in the infrared region. And what we see is that infrared region is going to be measuring, the energy is going to be associated with vibrations. So the vibrations here are what we're really looking at is bending and stretching, all right, compression and stretching. So if we look here, we're talking about these spring forces here pushing together, or the spring forces here pulling apart. And so these are the stretches. Now we can also have things where we move this way, bending, pulling, scissoring, different types of movements that are not necessarily associated with stretching and compressing, but perhaps changing the angle here. So there's a variety of different vibrations associated with the chemical bond. So what we can see is that there's different types, and we said there's different types of bending and different types of stretching, and that we see is these different types of modes are unique to each bond. And so what we can determine is the number of modes of bending and stretching can actually be determined through this equation. And so we say the number is going to be equal to 3 times the number of atoms minus 6. And so let's say we take a simple molecule such as benzene. Think about how many different atoms are in this molecule. We here have 6 carbons and 6 hydrogens. So there's 12. So it's 3 times 12 minus 6, which means we have 30 different modes of vibration for a molecule as simple as benzene. So the point here is that IR gets very complicated quickly, and you can only pull so much information out of this particular spectrum. And so we look at two different regions, and the one that we're most interested in is the stretching frequencies. And the stretching frequencies range from 1600 to 3500 reciprocal centimeters. All right, this is to the left of the IR spectrum. The fingerprint region, on the other hand, is more towards the right, and it is in the range of 600 to 1400 reciprocal centimeters. This region is full of stuff, and it is very difficult to interpret. So it's not that we can't find information in this region, but it doesn't give us the kind of detail that we're looking for, or definitive properties as we see in the stretching frequencies. All right. One other point that I'd like to make is that the IR frequencies are usually strongest for polar bonds, and the reason behind this is that, and that's stated here, the reason behind this is that the IR, the infrared, is essentially light, and light has magnetic and electrical components to it. So the light is better absorbed by things that are polar and have certain magnetism and electrical separation. So nonpolar bonds do not absorb well. So for example, a CO stretch will absorb much better than, let's say, a fluorine-fluorine stretch, because there is overall zero dipole for a fluorine-fluorine bond, but there is significant bond polarity for this carbon-oxygen. To take that one step further, if we compare our carbon-oxygen double bond to our carbon-carbon double bond, you'll actually find that they absorb in the same region, but the carbon-oxygen double bond absorbs significantly stronger. And so let's look at this table here from another source, and what it gives us is an idea of the frequencies for certain stretches. So if we take a look at our carbon-hydrogen and carbon-carbon stretches, carbon-hydrogens absorb somewhere around 3,000, whereas a carbon-carbon bond absorbs around 1,200. Now it takes more energy to excite a carbon-carbon double bond because it's stronger, and so you see that moves from about 1,200 to about 1,660. The carbon-oxygen double bond absorbs around 1,700, very similar to the carbon-carbon double bond, but is significantly stronger. Same thing for a carbon-oxygen double bond. And we see that there's a varying increase in the frequency as we move towards more bonds. And that makes sense because there's a stronger connection between those two atoms, so it requires more energy to stretch them. So we take a look at what an IR looks like. This is the IR spectrum of methanol. And so, again, very few atoms. We have 8 atoms here, I think. 4, 5, 6, 7 atoms. So, 6, excuse me. So what we have here is an OH stretch, CH stretches, bending, rocking, scissoring, stretching, twisting. It's quite complicated for such a small molecule. So we can only take so much information out of these spectra. How an IR works, we're going to just briefly cover this. Basically, you have a sample, and you have a reference. And what you want to do is you want to look at the light being absorbed as it travels through that spectrum and see what comes out on the other side. So some things will absorb more, some things will absorb less at different frequencies depending on the functional groups we have. Modern IR utilizes a concept called Fourier transformation, in that all frequencies of light in the IR region are passed to the sample at one time. And this is incorrect here. It should be deconvoluted by mathematical transformation. So that is really what's happening. You pass all light through the sample, and then various mathematical transformations will be deconvoluting that and produce the IR that we're used to. So the question becomes, well, what does it measure? Well, it measures various things, and so we can look at alkanes, alkenes, alkynes, other functional groups, and they all absorb at different regions. And so here, what we see is the position of some common functional groups. And you see down in the fingerprint region, we get a lot of single bonds, CC single bonds, CO single bonds, CN single bonds. And we also get various other things in there as well. The region right in here is a very important region between 16 and 1800. And we see that there is carbon-carbon double bonds, carbon-oxygen, carbon-nitrogen double bonds. This is definitely in the stretching frequency. And we see a strong peak here. We can learn a lot about a molecule. We also have this region somewhere in here, a little further up, where we have carbon-carbon and carbon-nitrogen triple bonds. Again, triple bonds take more energy to excite, and therefore they are higher in frequency, more energy. And finally, very high up are the carbon, oxygen, and nitrogen single bonds to hydrogen. And this we can tell a lot about a molecule based on what comes out here. So here we go. We begin with the functional group, the alkane. We see our CH stretches, and we also see our CH bending. Notice we don't see a lot of carbon-carbon bonds, again, because they're not polar at all. Even these are not very polar, but there is still some polarity to the CH bond. So very simple IR spectrum. If we move on then to the alkenes, we start to see some changes. And we see that there is a unique stretch above 3,000. And that is associated with an sp2 hybridized CH, and that is most often associated with an alkene. We still see our CH stretches for an sp3 hybridized carbon, and those are again below 3,000 reciprocal centimeters. So, and we also start to see a very tiny CC stretch, again, not polar, so it doesn't show up very well, around 1660. Again, alkenes, we see above 3,000 right here, associated with our carbon, hydrogen, sp2 hybridized systems, a CC double bond, and we have plenty of alkane groups, and so we still see our CH stretches below 3,000. Finally, to finish out, I want to briefly talk about conjugation and what it does to electron density and how that affects the IR. If we take a look at this, a carbon-carbon double bond will stretch somewhere around 1640 to 1680 reciprocal centimeters on a regular double bond. That drops to 1600 in benzene. And that's because benzene has this resonance where you can move electron density around. And so what does that mean about the properties associated with this bond? This is not a full double bond because those electrons in that pi system have moved. So we don't have a full double bond. It's not nearly as strong in terms of its stretching, so that the ability to stretch those CC double bonds gets easier, and so the frequency goes down, less energy required. So anytime you have resonance involved, you usually are lowering the energy required to stretch those bonds. We'll stop there and pick up more functional groups in the next lecture.